So I've learned the product and quotient rule, and now I want to apply them to a different kind of problem. Namely, I want to figure out where this function has a horizontal tangent line. You can see I've already labeled my function a little bit. So I have this portion over here, which is the u portion. So I'll call that function u, which is just the t. And then v is just the e to the t. Now this is a case where I'd rather use u and v than f and g because my function itself is named f, and that can get really confusing. So I'm using product rule. Product rule is rule number 7. I'm taking u, v, so that's u prime v plus u v prime. So this is u prime right here, right there. There's u prime. There's v, right there. Let me label it. That's v. That's v prime. And then this was u prime, and this was u. Right? So I'm using product rule, which is rule number 7, to make this work. And then I just kind of cleaned it up a little bit. We generally put, the one with the variable in front, so I put it in front, and nobody writes 1 if they don't have to. This was not necessary. You didn't have to come over here and do this. But it helps. So now I want to think about a horizontal tangent line. A horizontal tangent line would be when the derivative would be equal to 0, would have f prime of t equal to 0. So that's what we're going to do. So I'm going to take that derivative that I just found, so t e to the t plus e to the t. I'm going to set it equal to 0. Okay, so now I need to use algebra, right? And use algebra to solve, right? Use all the tricks that you know from pre-calculus. All right, well, if I look at these things, this is e to the t times t plus 1 equals 0. I factored e to the t out. Okay, well, two things multiplied to 0 means either this is 0 or t plus 1 is 0. But the one on the left is impossible. If you try to take the log of both sides, you get the log of 0, which cannot happen, right? So this is impossible, does not exist. Right? You cannot take the log of 0. There is no exponential function that will ever intersect the x-axis unless you give it a vertical shift of some kind. So this would be t equals -1 because you'd subtract 1 from both sides. So there you go. So there's t equals -1. Now the question is where? Where is a little confusing. I should change that. I should say at what point. So let me just go back up here. At what point? I'll fix that for future. At what point does the graph? Well, we have the x-coordinate. We don't have the point. So let's go find the point. That'll be step 3. These are our steps in case you're missing it. So let's find the point. Well, we have the t-coordinate, t equals -1. So we just need to have the f of t value to go with it. So we know it's -1 comma something, right? We just need to figure out the something. All right, so to do that, I will find f of -1, not f prime. F prime of -1 I know will be 0. I just proved it right here. The derivative is going to be 0 because it's going to have a horizontal tangent there. I want f of -1. F of -1 would be -1 times e to the -1, which would be -1 over e to the 1, which we know is -1 over e. So that's what we will have right here. And that would be the exact answer. If you want a decimal approximation, you have a calculator or a computer, you could find it. Just to give you an illustration of what's happening here, we have our function t e to the t that you can see, which is that black curve right there. And then if I have the point -1, -1 over e, allow me to grab the tangent graph and you can see. If I do this, there it is. See it? When it hovers over that blue spot, it becomes horizontal, right? The tangent line becomes horizontal. In other words, if I graph the derivative, which would be f prime of t, y equals f prime of t, notice that spot right there, -1, has a derivative of 0, and that's why it has a horizontal tangent here. There's the derivative graph. That's why the horizontal tangent right there at -1 is happening, because that derivative is 0 there. In other words, that spot right there, -1 over e is a relative minimum, right? And that's what we just proved over here. And I drew a little quick sketch of it as well, just so we could see, right? That little spot right there. All right, so now let's find the equation of the line tangent to the curve y equals 2x squared over 3x minus 1 at a equals 1. So I want to find the tangent line right there. I want to verify it graphically because Desmos is my friend. All right, so let's start by finding the derivative. So the equation of a line, let me just remember, is the tangent line, excuse me, is y minus f of a equals f prime of a times x minus a. We already learned that in section 3.1 and it's still true. All it is the point slope form with the derivative getting you your slope and a and f of a being your point. Okay, well, a couple of things. I'll notice that my a is equal to 1 right here. So a is given as 1 right there. So let's go find f of a right now and just kind of get it over with, because we know we're going to need to. So f of a is going to be f of 1, which will be 2 times 1 squared over 3 times 1 take away 1, which would be 2 over 2, which is 1. So this is f of 1. So I know that this number right here is going to be 1, and I know that number right there is going to be 1. I mean, for different reasons, but nevertheless, it works out. Okay, so now all I need is the f prime, and I'm grand. Right, so I know this will be 1, right, because this is f of 1 equals 1. And I know this will be 1 because a equals 1. So let's just go find f prime. Easier said than done. So f prime of x would be, and then this has got a quotient to it, so I'm going to use the quotient rule. So f prime of x would be 3x take away 1 squared, 3x take away 1 right here. Always take your denominator, put it here in the front and here in the denominator and square it. Now I want the derivative of my numerator. Well, my numerator is 2x squared, so the derivative of that is 4x. So there's my numerator squared. If I called it f and I called this down here g, I have g squared here, g right here, and then I just found f prime in my head. Then I'm going to subtract. Right? It's very important that you alternate g and f prime, and then you subtract, unlike the product rule where you add. All right, then I want f. F is just 2x squared. So there's my numerator, f. I could use f on this one because I didn't name the function f. If they'd named it f of x over here, then I would have called it u and v, just for convenience sake. All right, and then I want the derivative of the denominator, but the derivative of the denominator, that's a linear function. That's a diagonal line. So the diagonal line's derivative is the slope, which is 3. I mean, another way you can think of it is you're using the product rule, or excuse me, the power rule. This is to the 1 power. 3 times 1 gets you 3. X to the 0 is constant, 1. So that would be 3 times 1, which indeed is 3. So this is g prime right here. All right, so we don't have to simplify. I mean, all we want out of this is the slope. So we just want the slope of the tangent, which will be f prime at, well, technically this is the slope of the tangent at any x value, but I want the slope of the tangent at x equals 1. So I'm going to find it at 1. So I'm just going to stick 1 into this thing. So 3 times 1 take away 1, 4 times 1 minus 2 times 1 squared times 3 all over 3 times 1 take away 1 squared. Ugh, it's almost more trouble than it's worth. We could have done this in our head. 3 times 1 is 3. Take away 1 is 2 times 4 minus 2 times 1 squared. 1 squared is 1, so that's 2 times 3 all over 3 take away 1 is 2 squared. So that'd be 8 take away 6 over 4, which would be 2 over 4, which would be 1/2. It's not the answer, it's just the slope. So the answer is y take away 1, because that was f of a, equals 1/2, that's the derivative we just found, right? That's our slope, times parentheses x take away 1, because that was what a was. Ta-da! Now if you want to rewrite that, I mean, you can do so. It would be, you distribute your half, right? A half times x, so this would be y equals 1/2 x. Take away a half plus 1 will be plus a half, like that. If you want a slope-intercept form. This is point slope form, that's slope-intercept form. So let's see if I'm right. So let me go grab Desmos. Okay, so here I have the function 2x squared over 3x minus 1. And you can see I have the point 1 f of 1 labeled, because I'm sneaky. But technically it's also the same as 1 comma 1. The beautiful thing about Desmos is I don't actually have to find it to be able to make it work. But it is indeed the same point that I found before. And then I have graphed for us the tangent line so we can see that it touches just at that spot, nowhere else. And if you want to verify, oh, and I'm doing that by using the basic rule, the formula, that it's f prime of 1, there's the slope, times x minus 1, and then I just add f of 1 to the other side. So it's point slope form slightly modified. But if you want to make sure that what we did works, you could say y minus 1 equals 1/2 times x minus 1. And you can actually just type in the equation in point slope form or slope intercept form if you want to check that. So y equals 1/2 x plus 1/2. And sure enough, they're all the same. They're all equal to that tangent line. So what we did was absolutely correct. And that's how to verify it with our lovely, lovely Desmos. You could also do it with your calculator. The problem is that the calculator won't graph this portion, the derivative, without actually having to find it. The calculator doesn't do that. So you'll have to do that on your own. But nevertheless, it does in fact work out. And the tangent lines that we came up with here, either one of them, either slope intercept or point slope form, they both work out as being the tangent lines through the point 1, or where x equals 1 to this function.